All right, pre-cal 11, let's get after it. Here we go. We got our video number 6 where we're going to dive into adding and subtracting radicals. So, what do we do here? Well, an important concept to consider is if you had 3 times x plus 2 times x, we know that the x represents the same value. It's a constant. And what you could do, technically, is we could factor that x out, right? And then what you would get is you would just add the coefficients together and you'd have x times 5, or we would write it as 5x, which is why we can just group those like terms together. Remember, we did that in grade 9. 3x plus 2x is 5x because x's represent a constant value. Now, not a constant as far as the number goes, but a constant value. It's not changing. X is x. It's like apples. We have 3 apples, we had 2 apples, we now have 5 apples. X is an unknown in that case, but it is a constant unknown because it's the same thing. Now, when we consider radicals, it's exactly the same. Remember that the square root of 2 is a number, right? It is an irrational number that repeats forever, so we write it as the square root of 2 because it's exact. Now, if you were to have 5 times the square root of 2 and add 2 times the square root of 2, well, the square root of 2 doesn't change. And again, we could factor that out if you wanted to see it more clearly. And now you have the square root of 2 times 7, which we say is 7 root 2, or 7 times the square root of 2. So you can group radicals together if they are the same index, so here square root, and the same object in the square. So in this case, a 2 and a 2. If you have that scenario, you can group them together just like we grouped terms like 3x plus 2x. So let's just work through some examples and see how this goes. Now, here we go. Object of the root needs to be the same. As you can see, this is root 27, this is root 12, this is root 8. We cannot multiply those things together. But if you recall from our simplification video, if we can find 2 identical factors, or because we're here we have all square roots, or in this case a perfect square factor, we can factor those out and simplify them first. Now, I think about perfect squares. One's redundant, so 4, 9, 16, 25. Well, I know that 27 is actually just the same as saying the square root of 9 times the square root of 3. And I know that 12 is the same as saying the square root of 4 times the square root of 3. And then 8, well, 8 is the square root of 4 times the square root of 2. And I picked those because perfect square, perfect square, perfect square. And now I can simplify that to 3 root 3 plus 2 root 3 minus 2 root 2. Now here I have the same root, so I can add those together. 3 plus 2, I have now 5 root 3, but this is different, so I need to know that I can't do anything to that, and I just have to stop right there. That is as far as I can simplify. That is my solution. So knowing where to stop is really important. So now here's another one. Well, again, I have a square root, so I know that 27 is root 9, and then you can write all the rest. Doesn't matter. Root 3xy. And then 8 is root 4 times root 2xy, because I'm just factoring out a perfect square root. So now I have 3 times 3xy plus 2 times 2xy. And you might be tempted to do anything more here, but you actually cannot. Because this, yeah, there's an x and a y in there, but that's 3xy, and here is 2xy. So those things are different, so you need to know I actually can't go any further than that. So important to make that identification. Let's look at some more. So, I have a perfect square factor in there. That's negative 3 times root 4 times root 3, because 4 times 3 is 12. And oh, lovely, I now have plus 4 times root 25 times root 3. So now I have negative 3 times 2 times root 3 plus 4 times 5 times root 3. So now negative 6 root 3 plus 20 root 3. And now I have the same indexed root and the same object within it, so I can now combine them. Negative 6 plus 20, I get 14 and then times the square root of 3. Beautiful, lovely. That's how we do it. Now, watch the root index, because now I'm looking at a cube and a cube. So I'm not looking for perfect square factors anymore. I'm looking for perfect cube factors. So for perfect cubes, we have 2 times 2 times 2 is 8, 3 times 3 times 3 is 27, 4 times 4 times 4 is 64. So they're a little bit more sparsed out. But 16, I know, is the cube root of 8, and then times the cube root of 2. And then 54 is going to be, oh, look at that, 27 times 2. So the cube root of 27 times the cube root of 2. And now I can simplify because that's just going to be a 2. So now I have 2 times the cube root of 2. And then this is going to simplify to a 3 times the cube root of 2. And now I have 4 cube root 2 minus 9 cube root 2. And now again, same. So 4 minus 9, I have negative 5 times the cube root of 2. So you need to make sure you have the same root index and you have the same object underneath that root, and then you're good to go. Sometimes it's not going to happen, like in both of these examples, and you need to know where to stop. So one more. These look a little bit more loaded, but we can notice here, square root, square root. So at least our root index is the same. So what we're looking for is we're looking for perfect squares. Well, r squared is a perfect square. And then t cubed is the same as t squared times t. So I have a perfect squared hanging in there too. Now 20 is 4 times 5. 4 is a perfect square. And 49 is 9 times 5. So perfect square. So I got some wiggle room here. So now root 3, I'm going to write this sort of in different factors of perfect squares. Root 4 times root 5 times root r squared times root t, just to show you that everything underneath the root can be written as individual roots. Then minus 2 times root 9 times root 5 times root t squared times root t, just to show you the breakup of the t cubed, because now I have perfect square, perfect square. These two are not, so they'll stand to the root. So I have negative 3, and then times 2 times r, and then I'm left with 5t underneath. And then here I have perfect square, and again I'm left with 5t, so that's looking promising. 2 times 3 times t times 5t. So now I have negative 6r times root 5t minus 6t times root 5t. So now you might be looking at this thinking, well, the 5t is the same and the root's the same, and that is correct. But here we have different things. We have an r here and we have a t here. So we are technically all done. We cannot simplify any further because we can't combine the negative 6r with the negative 6t. So be aware of different variables all over your equation. Now the last one, 32. Well, I know 32 is 16 times 2. 16 is a perfect square. 48. Well, I know that 48 is actually 16 times 3, so I have another perfect square. 50, well, that's 25 times 2, and 27 is 9 times 3. So I've identified perfect square factors. If you need to go a different route, you need to go, okay, well, 48 is 2 times 24, which is 2 times 12, which is 2 times 6, which is 2 times 3. You'll be like, okay, well, here's 2 perfect squares. You can find it. You'll just get a little bit better at identifying perfect square factors the more you do this stuff. So 32x becomes, the 16 breaks out is 4, and I'm left with 2x underneath. And then the 16 breaks out here as 4, and I'm left with 3y underneath. And then the 25 breaks out as a 5, and again I'm left with a 2x underneath. And then the 9 breaks out as a 3, and I'm left with 3y underneath. And now we can rearrange our statement here. I have 4 times root 2x minus 5 times root 2x. We're just grouping like terms again. And I have negative root 2x. And then here you have 4 times root 3y and 3 times root 3y, so plus 7 root 3y. Generally, we want to keep things in descending order with our variables, so that would be fine. But if you really wanted to, you could definitely rearrange this equation so you don't lead with a negative, but totally up to you. Those are equivalent statements. So that is how we go about adding and subtracting radicals. In the next video, we're going to look at multiplying and dividing them, and then we're going to look at how we can solve them. Okay, thanks so much, and I will see you next time.